Hello friends, welcome to our channel, and in this video we are going to learn about the bending of beam and the bending moment of a beam. Right. So first of all we will see what is bending of beam and then how to extract the bending moment. If you remember in the last video, that is in the cantilever video, we have used this bending moment, but actually this video has to be before that video, but yes, by default, or by we can say I have posted it earlier than this, but this should be first of all learned and then we should go forward cantilever. Okay, so yes, I will post the link of the cantilever video in this video description box, so you can watch first of all this video and then I suggest you go to the cantilever. Okay, now or it doesn't matter, we just have to use the bending moment whatever we have derived in this particular video, today's video, that we have used directly in the cantilever. That is why I said this video has to be taken before that video, but otherwise it's okay, right? If you know how to get the bending moment. But first of all, we'll see what is bending of a beam. Yes, a beam is what we call a structure, a long structure, whether it is a rectangular in cross section or we can say in cylindrical again, or a circular cross sectional, right? So that we call as a beam. And firstly we will see what is bending of beam. So when we say a beam is exactly horizontal without bending, the first diagram we can say without bending, that means if we have a beam which is supported by these two particular supports and we do not apply any force on the beam, so it was of length L, whatever we showed, right? And the central axis, actually the beam is made up of several layers we can say, or several thin filaments, we call them as filaments. So if a beam is considered to be made up of the number of filaments, then the central filament basically we call it as neutral axis. This central filament we call it as neutral axis. Okay, so when we are just looking at a beam which is kept at equilibrium without experiencing any force and all, its length as well as the neutral axis remains same. But now see in the second diagram, now this is with bending. With bending, so what we have done for the bending, we have applied force from this side, right? Or you can apply force from downside also. In that case, the bending will be in upper side. Okay, so here what we have done, we have applied the force from upper side at the center of that beam which is supported at both the ends. So what exactly happens, the beam has been bended in this direction, right? And it forms an arc of a circle, right? Can you see, this is what, an arc of a circle, it is almost arc. Okay, so it forms an arc of a circle, and if we carefully observe the axis, that is what the central axis, what we call the neutral axis, does not have any extension or the compression, but now in this particular case the filaments which are below this neutral axis will have elongation, we can say they have extension, and the filaments which are above this neutral axis will have compression, or what we can say they have, or they undergo the contraction, right? But the neutral axis or the central axis remains as it is without any extension or contraction, and that is what we call it as the neutral axis. Okay, so that is what we can say the bending of beam. That means what happens now, if I am talking about in reverse manner, if we are applying force in downward direction, then what will happen? Now let me draw a little bit zoom diagram. Okay, so if we say this is a neutral axis, dotted line, and if we are applying force from downward direction, then in this case this neutral axis will be x. So the filaments which are above the neutral axis will have elongation, or they will have extension, we can say, or they will stretched or extended, and the filaments below the neutral axis will have contraction. They will have the contraction, or what we can say, they will get compressed. They will get compressed. But now whatever we have shown in this diagram here, the filaments which are below the neutral axis will have elongation, right? Let me write here, or extension, and the filaments above the neutral axis will have contraction, we can say, they will get contracted. Okay, so such a thing we call it as bending of beam, right? So this bending actually occurs, or this bending actually leads to the tensile linear strain or linear stress in the beam, or more in the filaments of the beam. And therefore the question arises, whenever we are having stress or strain came under consideration, then yes, obviously we will talk about the Young's modulus, right? So obviously it is linear or tensile strain, that's why only we are talking about the Young's modulus, right? If it is about volume, we will go to the bulk modulus, and if it is about the shearing stress and shearing strain, then we will go to the modulus of rigidity. Already we have found the modulus of rigidity by torsional pendulum. Again, I will post the link of that video also in the description box of this video. Okay, watch all these videos, then you will understand what is tensile strain and what is shearing strain and all. Okay, so what I am saying, due to this bending only, this bending leads to the tensile stress or strain, and then we have to come across this bending moment. Okay, so first of all, let us understand what is I hope you got the point, what is actually the bending of beam. So the bending is simply we are applying some force, and due to the application of that force, some filaments will get contracted and some filaments will get extended, but one filament which is at the center remains constant, remains unchanged, and that is what we call the neutral axis. Okay, so it depends upon in which direction you are applying the force, the filaments above and below the neutral axis will get extension or contraction. Okay, right. Now in this particular case, above the neutral axis we have contraction, and below the neutral axis we have the extension. Okay, right. Now let us see specially the bending moment of beam. So by using this concept, let us find the bending moment. So again, for bending moment, let me draw one more clear diagram, and so that we will have some clear understanding. Okay, now so come to this diagram, second diagram. Again we have drawn little bit zoom diagram. So see, this AB is a neutral axis. AB is a neutral axis. Obviously we are applying here force from downward direction. Here the force direction is like this. So that means the filaments which are above the neutral axis. Now here we have taken A1, B1, that is the next successive filament after above the neutral axis. So that axis, that filament got extended or elongated. So obviously, and the filaments which are below that AB neutral axis will have some contraction. So but either you can take the extended or contracted. So for our consideration purpose, for our experiment purpose, here we have taken the filament which are next to the or above to the neutral axis, that is A1, B1. Okay, and the separation of between the neutral axis and that filament is we have taken X. Okay, now this obviously due to application of the force, this again A, B or the beam itself forms an arc of a circle, and let us consider the center of the circle is O and with the radius of curvature R, Okay, so let us take the smaller portion PQ of neutral axis, which makes an angle theta at the center, and similarly if we extend that PQ, or we can say OP and OQ towards the or till the first what we can say the filament A1, B1, and then again obviously we got P dash Q dash is again arc of that circle or that filament, and it also forms an angle, or it also subtends an angle theta at the center, but the radius of curvature is R plus X for the P dash Q dash arc, right? Now when we know the arc and the radius of curvature, then easily we can find the angle. Yes, so the basic formula to get the angle from arc and radius, simply arc upon the radius. So for the arc PQ, now I am talking about the neutral axis. For neutral axis, arc is PQ for our observation purpose, this arc. Okay, so this arc PQ can be written as, or for this arc we can find the value of theta. Theta is equal to arc upon radius by this general formula. So arc is PQ and radius of curvature is R. So this gives actually the value of PQ. PQ is nothing but R into theta, equation number 1. Okay, now similarly just talk about the arc P dash Q dash. So for P dash Q dash, what we get is, for that means for filament A1, B1, P dash Q dash is a portion of filament A1, B1. So for P dash Q dash, again theta angle is same. So arc is P dash Q dash, but the radius is now up to this point P or Q, the radius is R, but filament A1 B1 is at a distance x from this neutral axis, so the radius of curvature has been increased by x. So R plus x is the radius of curvature, and therefore here we got P dash Q dash is equal to R plus x into theta, equation number 2. Now what we got is PQ and P dash Q dash are the arcs. Obviously they have some changed, right? And obviously P dash Q dash has been elongated. So how much is the elongation? How to calculate? Simply if we subtract that extension, means if you want to find the extension in the filament A P dash Q dash, then simply subtract that arc value P dash Q dash, or let us take the subtraction of P dash Q dash and PQ. If we take that subtraction, then we will get how much will be the extension takes place due to the application of this restoring force in the filament A1 B1. So the extension, simply we can get extension in P dash Q dash is equal to P dash Q dash, that is arc whatever we got in equation 2, minus arc PQ of that neutral axis, which is got in equation 1. So P dash Q dash value R plus x theta minus R theta, and if we subtract them by simply separately multiplying, then we got x into theta. So this is what actually the elongation or the extension takes place, right? Extension or elongation takes place due to the application of this force in the filament A, B, or more, or what we can say the portion whatever we have considered is P dash Q dash. So equation number 3, this much is the elongation, x into theta. Okay, so this is what the change in length. Elongation means we can say obviously the length has been changed. We can write it as delta L, right? Delta L, change in length. And obviously the original length of the filament is what? Or originally how much was the length? It is PQ. Original was PQ, right? So therefore we can write here the tensile strain. Strain is nothing but what? Change in length upon original length, or extended length upon original length. So the extended length or extension is x into theta, and original is what? Original PQ only, and what is that? R into theta. So x theta divided by R theta, theta theta will get cancelled, and what we get is the x by R, and this x by R indicates the linear strain. So one of the parameter we got among or from the Young's modulus, that is strain. Okay, now obviously we must know the stress. So let us go to the stress. So linear strain we found is x by R. X is simply the distance of that filament from the neutral axis, and R is the radius of curvature about the neutral axis only, right? Now name it as equation 4, and let us go towards the stress. So if we are talking about the filament P dash Q dash, and let us consider its area of cross section is delta A, smaller area of cross section. If delta A is the area of cross section of filament P dash Q dash, then obviously the linear stress we can find force upon area, force per unit area. F is the restoring force, or whatever we are applying, F is a force, and delta A is the area of cross section. So simply linear stress is F divided by delta A, equation number 5. So equation 4 gives you the linear strain, and equation 5 gives us the linear stress. So let us take their ratio and find the Young's modulus. So Young's modulus is simply linear stress upon linear strain. Linear stress upon linear strain. So linear stress F by delta A from equation 5, and linear strain is x by R from equation 4. And if we rearrange, that means F divided by delta A as it is, and this capital R numerator or denominator's denominator will go to the numerator, and therefore F divided delta A R by x. Or we can find the value of F. Why we are finding F, you will come to know, because we want bending moment, and bending moment is nothing but force into x. But therefore just rearrange and get the value of this F. So by rearranging we can get y as it is delta A into x by R, and this F indicates the restoring force. Name it as equation number 6. So equation 6 indicates the restoring force acted upon area delta A of the filament P dash Q dash, right? It is simply which is the restoring force applied on this much delta A area of the filament P dash Q dash. Young's modulus. Why is Young's modulus? X is what we know, the distance between that filament and the neutral axis, and R is the radius of curvature, right? Now if we know the restoring force, then simply we can talk about the bending moment. So the bending moment due to this restoring force in the P dash Q dash, filament P dash Q dash, is simply M is equal to F into X. F is the restoring force and X is again the distance of that filament from the neutral axis. So F, we can substitute the value of X from equation 6. So equation 6, y delta A X by R. Already X was there and this X square, and therefore this bending moment becomes, or we can increase one more step here. So F is what? Y into delta A into X by R, and this X. So this X and X becomes X square Y by R as it is into delta A, equation number 7. This represents the bending moment. But bending moment for what? Bending moment for that filament only. Which one? P dash Q dash. Okay. Now if we want to find the total bending moment of the beam, we should take the algebraic sum of all the bending moments for every filament. So therefore the total bending moment we can simply get by taking the algebraic sum. By taking algebraic sum of bending moments of all the filaments, right? So simply bending moment total can be written as summation y by r into X square into delta A, because this is what? For the filament P dash Q dash. This is for filament P dash Q dash, but this is now for total beam. This is for the beam, right? Now y Young's modulus and radius of curvature of that particular arc will be constant. Let us take it outside of the summation, and summation X square into delta A, y by r summation X square into delta A. Again delta A is the area of cross section of that filament, and X is what? Again the distance of that filament from the neutral axis, right? Now what this exactly indicates, this particular summation X square delta A, that is actually represents the geometrical moment of inertia of the beam, and therefore we name or we indicate it by Ig, I suffix y by r as it is, and Ig what we call is the geometrical moment of inertia, geometrical moment of inertia, and that is what actually summation X square into delta A. So that indicates the geometrical moment of inertia. Okay, but that geometrical moment of inertia is again only for this delta A is a cross sectional area of what? Only that arc P dash Q dash or filament A1 B1. Okay, but now if we talk about the total beam, then the geometrical moment of inertia can be written as Ig is equal to A into K square. So A is what? Now the total cross sectional area of the beam, not only for the filament, but it is now A is total cross sectional area of the beam and K is radius of gyration. So how to get this radius of gyration? I have given here. So this radius of gyration, simply K is equal to under root I by M. Now this is what? Moment of inertia about the axis which is perpendicular to the length. Okay, and M is what? Total mass of the beam. If we want, we can write it as small m also. So this, once you know the K, that is the radius of gyration, and if you know the dimensions of the beam, that means from the dimensions we can exactly get the total cross sectional area. And if we know both these values, then we can get first of all Ig, that is geometrical moment of inertia, and if we substitute this Ig to this point, that means in equation 8, and if you know the Young's modulus and radius of curvature, then we can easily get the bending moment. We can get bending moment. So this is actually the formula, general formula to get the bending moment of a beam. Bending moment of a beam, right? Now let us see what is conclusion of this particular video. So the conclusion is simply we found the bending moment M is equal to, this is what? This is bending moment. First of all, we have seen what is bending of the beam, and now what is bending moment? So bending moment we found is that M is equal to Yig by R, and if you remember in the cantilever video we have taken this as directly, and that's what I initially said, this comes from this derivation. Okay, you might got question there from where I have taken directly, but actually this has to be learned first before that cantilever derivation. Okay, so the bending moment we have here taken from this directly Yig divided by R. So this is what bending moment for a beam. Y is Young's modulus, Ig is geometrical moment of inertia, and we know how to get that, and R is what? Radius of curvature. So what is conclusion? This is what the formula we found in this video, and if we look at the formula, so we found one important thing, that bending moment is independent of length of the beam. Length of beam. So the length of beam does not affect upon the bending moment, right? And moreover, the bending moment is directly proportional to Young's modulus and the geometrical moment of inertia, and moreover, the bending moment is inversely proportional to the radius of curvature, right? So this is what actually the conclusion of this video, and I hope you got the points. If you have any doubt, you can post in the comment box. Otherwise, if you feel this is value addition to your knowledge, then like this video. For more such videos, subscribe to our channel, and yes, press the bell icon so that you will get notifications of our next videos, right? So yes friends, this is what about the bending moment and bending of beam. I hope you got the points, and we will meet in the next video with new concept. Till then, take care of yourself and keep learning, keep watching. Thank you so much for watching this video. Thank you.